All right, so this is where we left off, and we were talking about the disaster of Agent Orange and how the GC world would be perfect to analyze those types of samples to measure and monitor the TCDD levels or dioxin levels or any type of environmental concern. The problem, though, is that, like we said before, many times in a laboratory, we do not get a very clean sample, right? We always get these mixtures of samples, and the mixtures of samples have to be separated. So, for instance, one of the samples that you might get would be a gasoline sample. So go to your gas pump, pump into your fuel container, a liter or a half of a liter of gas, and bring it into the lab and analyze it. The problem is that gasoline is made up of many components. There's many different compounds that make up gasoline. On average, there's anywhere between 70 to 120 of them. How on earth do we analyze something like this in a laboratory? 70 different components in that one mixture? Well, the GC can separate these, and the GC does a very good job in doing it as long as you make the proper settings. So the GC will, one by one, separate these things out, and it will begin to analyze them. So one component comes out, and it gets analyzed, and then we report that data, and then a second component comes out, and we begin to analyze that one. And then a third component will come out, and the GC will analyze that one. And it will do that for everything that's inside of the system or the sample itself. So what does the data look like? 60 different components. These things get busy. So what you're seeing here is a chromatogram. And the chromatogram represents the number of different compounds that it has found in your sample that was analyzed. So this is just a part of a gasoline sample, not everything, just a part of it. So down here at the very bottom, you'll see an increment. This increment is in terms of time. So 0 minute, 4 minute, 8 minute, 12 minute, 16 minute. You actually see the unit down here at the very bottom. For almost all chromatograms, time is the unit on the x-axis, right? And that's pretty important to kind of remember. So when I get data from the GC system, almost every time is down at the bottom. Now these can come in minutes or these can come in seconds. It can be any unit of time that it wants, but typically these are reported in terms of minutes because that's typically the run time. These are minute run times. They're not second run times, and they're not hour run times. These are in terms of minutes. So that's the number that goes onto the bottom. So what happens is that the GC will take your mixture, and this mixture will begin to be analyzed. Well, it takes some time for the mixture to go through the machine, and this creates what we call the baseline, or in the beginning, this is just flatlining out at the 0 mark. Okay, and then sooner or later, one of these components will come through the machine and be seen by the instrument itself. And when that particular component's seen, we see a huge peak that begins to get formed on the chromatogram itself. And then sooner or later, that peak has to come off. And when that peak comes off and there's less and less and less and less of it, we see this graph come back down to the starting line. All right, we call that a peak. That peak represents one particular component. And then if your sample only has one component, that's the only one that you'll see. However, we also see that there's multiple things inside of our sample. So sooner or later, my red portion will come off, which represents my second component. And when that comes off, the instrument will see it. And then it will slowly come back off as there are less and less and less of it. And it will come back down to the baseline. So that represents a second component that the instrument has seen. Finally, in this example, we've got a third component here. That's this green one. So sooner or later, my green one will come off, and up it goes. The detector's seen it, and then it comes back down to the baseline. So this sample shows three different components that make up the mixture. And that's what the purpose of the chromatogram is. So in this slide, what you're seeing is really a zoomed out portion of what we call the chromatogram. And each one of these peaks represent a different component all the way through. Gasoline can have over 100 different peaks. Over 100 different things can be picked up using a sample such as that one. That's pretty astonishing when you think about it. However, for your purpose, you won't really be seeing that many peaks. Most of the time, we have devised a sample that has a limited number of peaks to really simplify this process down. So the proper term that we use for this type of chart is called a chromatogram. And all chromatography instruments make a chromatogram. And GC is no different than any of the others. So when we ask you about chromatogram, this is the graphical representation that represents the number of different components that are inside of that mixture. And from this one, we will take away there's three components in the mix that was given to me. Now, the axis here on the y-axis, what unit is that? This can be different. So what we'll do here is we'll just put signal. And sometimes we represent signal with an A, just to kind of give it a variable. If you take a look at the chromatogram that's in the slide, you'll see that there's no y-axis that's there. And that's again because this can slightly change depending on what type of GC that you're running. But it's some type of signal. Some type of detector is on the machine detecting things in a way that might be slightly different than another detector. And because of that, that unit will fluctuate. It will change depending on what you're using. So that's the chromatogram. This is the type of data that we will begin seeing on the GC when we begin running it. And this is what you'll see when you start doing your laboratory practicals as well. Now, there are limits to GC. We've already talked about many of these. First, it has to be volatile. Second, it has to be stable in a gas form. We call this thermostability. That means when you heat it up and turn it into a gas, it has to stay as a gas and it cannot break down, whatever you decide to do. It cannot break down. So if I've got this sample that I am heating up and this sample begins to volatilize and make a gas, that's great. That's the number one criteria. You have to turn it into a gas. However, the second thing is that it has to stay in a gas form. And if it stays in a gas form and it does not break down, then this is a perfect candidate for gas chromatography. The problem is that sometimes when these things are heated, this can break apart and we can get fractions of the molecule that was there at some point in time. And you don't want that to happen. You want the molecule to stay together. That way it can flow through the machine as that particular compound and be detected as that particular compound. Second, it's not really good for qualitative analysis. Qualitative means just identification purposes. And the reason I say this is because numbers are great, and we do a lot with the numbers. That's quantitative analysis. But if I don't have a standard or something to compare my sample to, then when I go back to these peaks in a gasoline sample, I will have no clue what these peaks are supposed to represent. And I won't until I actually have those particular components and run them by themselves to see if number 4 was pentane. Well, I would need pentane only in a laboratory, a standard of just pure pentane, and that's it. And I would need to inject pure pentane into the chromatogram. And then I would be able to kind of go through and say, all right, the times and the peaks kind of match. So number 4 probably is pentane. All right, that's qualitative analysis. And qualitative analysis is very difficult sometimes on gas chromatography unless you have a mass spectrometer. Now, our laboratory does have a mass spectrometer. You will get to use a mass spectrometer if you're in our program, but probably if you're part of the competition, you might see the mass spectrometer in the lab, but you probably aren't using it. If you're one of the lucky teams, you might be. But that's what we call the Ferrari of our laboratory, as it's typically the most expensive piece of equipment that we have. Okay, so this is where I'll stop. And in the next video, we'll talk about what makes a good candidate for a sample before we talk about pieces and parts, and a little bit of manipulation that we can do in a laboratory to see if we can make the sample behave better in the GC system.